Hello everyone, welcome back. So this is your second lecture of intermediate MME. In the first class, we discussed about Leontief system of equations. ठीक है? और उसी में we also talked about an example where we had fish, timber and fishing boat. So similarly, we have a question for you, and the question is, consider an economy divided into an agricultural sector that is denoted by A and an industrial sector denoted by I. To produce 1 unit in sector I requires 1/6 unit from A. That means if A is to be produced, some component of A would be used as input itself. Further, 1/4 of the requirement would be of I. That means to produce 1 unit of A requires 1/6 of A plus 1/4 of I. Okay? So that is internal demand. That means internal demand would be per 1 unit of the production of good A, how much requirement of A would be 1/6 of A. ठीक है? और कितना रिक्वायरमेंट होगा I से 1/4 of I. Okay, so to produce 1 unit in sector I requires 1/4 unit from A and 1/4 unit from I. Similarly इसी तरह हम sector I का internal demand निकाल लेंगे. Suppose final demands in each of the two sectors are 60 units. So final demand, that means external demand, is given 60 units in both the cases. Write down the Leontief system for this economy. So proceeding to the solution. So solution would be, this is 12.1 exercise, question number 1, solution. So the solution would be, whatever the supply would be, that should match with demand. That means total supply equals to total demand, and total demand comprises of internal demand, that is ID, plus external demand. External demand was denoted by final demand also. Okay? So total supply, that means whatever the output is to be produced. Suppose we are talking about sector A. Okay? Agricultural sector. So for agricultural sector, you had A. That means for a production of 1 unit of A, you required 1/6 of A. That was internal demand of the good A was 1/6 of A per unit of A. Okay? So it will have the total supply of good A would be A, and A is used in the production of A itself and in the production of what? Industrial sector. Okay? That would be internal demand. So internal demand of A has an internal demand for A in 1/6 fraction, and for I 1/4 fraction. So the internal demand for this A would be 1/6 of A plus 1/4 of I plus whatever the external demand is there. So this is your external demand. This means all these terms give the total demand of industry A. Similarly, you will have total demand of industry I. So if you look at the question, so you will see I would be equal to 1/4A plus 1/4 I. In this case also the external demand is 60. तो सेम यही होगा, एंड इसी दो इक्वेशन को मिलाकर आप बोलोगे लियोन्टिफ सिस्टम ऑफ इक्वेशंस. ठीक है? जस्ट नोट इट डाउन. ओके? नाउ कमिंग ऑन टू द सेकेंड पार्ट ऑफ दिस क्वेश्चन. सो first part was write down the Leontief system of this economy, and second is find the number of units that has to be produced in each sector in order to meet the final demands. So to meet the final demand, what would be the total production? Okay, this was the question. So how much unit would be produced in each sector to meet the final demand? Okay, so this was part A. आप चाहो तो यही इक्वेशन एग्जाम में लिख सकते हो. अब उसके अलावा भी you can try rationalizing it and reducing it to simpler equations. So you will have, coming on to this, A as A minus 1 by 4, sorry, 1 by 6A equal to 1 by 4I plus 60. That would be 5 by 6A equal to 1 by 4I plus 60. So that would be one equation 1, and this will give I minus 1 by 4I equal to 1 by 4A plus 60. So you will have 3 by 4I equal to 1 by 4 of A plus 60 as your second equation. While trying to solve these two equations together, you will find the value of I and A. I and A was your total supply. Okay? So if you look at the first equation, you will have 60 equal to 5 by 6A minus 1 by 4I. Similarly, in the second equation, you have 60 equal to 3 by 4I minus 1 by 4A. Okay? So since both are equal to 60, you will have 5 by 6A minus 1 by 4I equal to 3 by 4I minus 1 by 4A. So you will have this I would be one side, so you would be having I in the right hand side, and in the left hand side you will have 5 by 6 plus 1 by 4. That would be 12, and it would be 10 plus 3. Okay, so that would be 13 by 12. So 13 by 12 A equal to I. So if you substitute value of I in any of these equations, then you can rationalize it. So if you put a value of I in the first equation, so you get at 5 by 6 A equal to 1 by 4 into 13 by 12 A plus 60. So this gives 5 by 6 equal to how much? So it would be 13 by 48A, here also A, equal plus 60. So if we take this down, we have 5 by 6, that means 48, or here it would be 40A minus 13A equal to 60. So you will have, it would be 27A equal to 60 into 48. So you will have A equal to 60 into 48 divided by 27. So it would be 9, it would be 20, it would be 3, it would be what? 16. So you will have 320 by 3. Similarly, you know that the value of I is equal to 13 by 12A. So you can calculate it as 13 by 12 into 320 by 3. So you will have, here you can write 3, it would be 80. So you will have 0, 8 into 3 you will have 24, you have 2, so you will have 1040 divided by 9 as the value of I. Okay, so whatever the requirement of the total production was, you will get A would be equal to 320 by 3 and I would be equal to 1040 by 9. Suppose you want to represent the production in industry A by say X. So you can write in place of A, X. In place of I, you can similarly use another notation Y. If you want to write in terms of X1, X2, then you can say whatever the production in industry A would be, that can be represented by notation X1. Similarly, whatever the production you have in industry I, you can write it as X2. Okay, so just take a note of it, and I hope you can similarly solve the other given questions of 12.1. If you find any issue, just let me know. Okay, now coming on to our next topic. Next topic is about vectors. Okay, so in your school you might have also seen what the vector is. When you had the thought of three diagonal planes, so you had three unit vectors. So suppose this is your vector, this is your x-axis, this is your y-axis, this is your axis z. So for x-axis you had unit vector, that unit vector in 3D space was represented by 1 0 0. In the y-axis it was represented as 0 1 0. In the z-axis it was represented by 0 0 and 1. We are talking here about the unit vectors. Okay? So the unit vectors have unit distance. Okay, that means their length is unit. So if you take under root of the sum of the squares of the coordinates, you will have 0 square plus 1 square plus 0, that would be 1. Similarly for this you can write 1 square plus 0 square plus 0 square, that would be equal to 1. And similarly for z. So in a 3D space, if you want to create any vector, that vector would be a linear combination of all these three vectors. So you had already talked about this in your school classes. Suppose we are given some vectors. So you have some vectors, and that vector can be represented either as a column vector or as a row vector. Always remember, column vector means we are talking vertically. Okay, and in the row vector we are talking about horizontal vectors. Okay, always remember this. So this is your row vector, this is your column vector. Okay, suppose if you have three elements mean 3 2 1, right? So if you want to write this as a column vector, then you can write 3 2 1 and use this parenthesis to represent the vector. Okay, similarly for a row vector you can represent it as 3 2 1. So your order will matter. Why the order will matter? Because we talked about the Cartesian plane and we saw that on a Cartesian plane 2 1 and 1 2 were not the same, just like the ordered pairs. Here also the vectors, if the order is changed, then the vectors would be different. That means 3 2 1 vector is different from vector 2 1 3. Similarly 1 2 3 vector is different from these two vectors. Okay. Suppose we want to check whether the two vectors are equal. So if two vectors are equal, in that sense, you will have all the corresponding elements of the vectors being equal. Okay? Corresponding elements of the vectors would be equal or same. So suppose I say a vector, say 3 2 1, this is one vector represented as a row vector, and another vector is 3 1 2. Although in these two vectors the three elements comprise of only 1 2 3, okay, but the orders are different. That means corresponding to the first element of the first vector, the second vector also has the same value, but while we compare the second and third elements of the first and second vector, we see that they are different. That means although the first elements of the two vectors are same, but the second and third elements are different. Okay, that means these two vectors are not equal. Okay, so when they would be equal? When in place of 3 1 2, if we had 3 2 1, okay, then also these two vectors had been equal. Suppose if you are given 3 1 2 and another equation as x, x1, x2 and x3. So if you are given that these two vectors are equal, so you can find the value of x1. How much the value of x1 would be? This would be equal to 3. Similarly for x2 you can calculate that the value of x2 would be 1. Similarly for x3 you can calculate that the value of x3 would be 2. So suppose these are the values that you can find by the equality, then you might be given that two vectors are equal. Okay, given two vectors as equals represented as 2 1 x, and say one I is x, y and 3. So you are asked prove that these two vectors are equal. So you will find that if you take the value of x from the first element of the two vectors, you get that x equal to 2. Okay, but you compare the third elements, you get that x equal to 3. Since x should denote the same value, but here you are getting two different values of 2 and 3. That means these two vectors are not equal. That means these two vectors are not equal. In place of this, if you are given 2 1 x and y z and say 3, and you are asked that these two vectors are equal. So find the values of x, y, and z. Since you know the two vectors are equal, that means the corresponding values of first vector should match with the corresponding elements of second vector. Okay, that means if you compare the first elements, you will have y equal to 2. If you compare the second elements, you will have z equal to 1. If you compare the third elements, you will have x equal to 3. Okay, so this is the case of equality of two vectors. Suppose if two vectors have different number of elements, that means if you have one vector represented by A that has 1, 2, 3, while you have another vector B represented by 3, 1, 2, 4, you know that the corresponding elements are not same, they are not equal. But what if you have a case of second vector being equal to 1, 2, 3, 4? So you see that the first three elements of both the vectors are same, but the fourth element is present only in the second vector. So this second vector is of 4D space, while the first vector is of 3D space. And you know that a three-dimensional figure can't be compared with a four-dimensional figure. Okay, so since the vector B has a fourth element, it is not equal to vector A. That means whenever we are comparing the two vectors, we must have same number of elements in those two vectors, plus the values of the corresponding elements in both the vectors must be equal. Okay? So just note it down. Now suppose you are given two vectors A and vector B. Suppose they both are of the same order. Okay, that means the number of elements in both the vectors are same. Okay, so first vector be represented by 1, 2, 3, 4, and second vector be represented by 4, 3, 1, 6. So if you want to find A plus B, that means the sum of the two vectors, then just remember, just like the way you were checking about the equivalence or the equality between two vectors, similarly for the summation part you will look after the corresponding elements. Okay, so you are having addition operation. Okay, so this addition operation here means A plus B should have the sum of the corresponding elements in these two vectors. So the sum of A and vector B would be the sum of all the corresponding elements in these two vectors. So the first element of A is 1 and the first element in B is 4. So the sum of these two would be 5. Similarly, for the second you will have 2 plus 3 equal to 5. Similarly, for the third element you have 3 plus 1 equal to 4. Similarly, for the fourth element you have 4 plus 6 equal to 10. So A plus B is 5, 5, 4, 10. That means whenever you want to have the addition operation, then you will add all the corresponding elements of the two vectors that you are given. Suppose if you had to find the difference of A and B, that means suppose you are given A and B and you want to find A minus B, then from the element A you have to subtract element B. So 1 minus 4 would be minus 3, 2 minus 3 would be minus 1, 3 minus 2 would be 2, 4 minus 6 would be minus 2. If you are to find b minus a, then you will have 4 minus 1 would be 3, 3 minus 2 would be 1, 1 minus 3 would be minus 2, and 6 minus 4 would be 2. So if you look at these two differences, that means a minus b and b minus a, you are seeing that these two resultant vectors are different. Why? Because this a minus b and b minus a are not commutative. Okay, that means a minus b means a minus b means a plus minus of b. That means you are adding the minus of b, and you know, suppose a vector has this direction, then the negation of this vector would be just of the opposite direction of the same length. Okay, so suppose this is vector a, then this is vector minus a. Suppose this is vector b, then in the same parallel fashion you will have another minus b, but with the opposite sign. Just assume that these two vectors are parallel to one another but with a different sign. Okay, and the length of the two vectors would be same. Okay, so if you want to add two vectors, suppose this is a vector a from point, say any point O, this is vector A, and if you want to add b in it, then the tail of vector b must be added from this point. So you will have b here, so whatever the final outcome from the initial point is, this is your a plus b. Suppose you want to find a minus b, so this is your a, but you want to find b in minus. So how will you find that? So you see that a plus b we used to add the tail of vector b to the arrow of a. So you want to subtract b from a. So if you want to subtract b, that means it should be subtracted from a. That means here you won't start. From where you will start? From this point. So you will have a plus b, assume that this a and this is b. So this, the resultant thing that you are getting is a minus b. Getting my point? This is what a minus b in geometric terms is. Okay, now you would now you may ask what the direction of this a minus b should be. So you have confusion like that, whether to have a minus b in this direction or to have this in this direction. So you know that you have a in this direction, a is in addition. So similarly, minus of b should be in downward direction. That means minus of b would be in opposite direction. Okay, so you will have something like this direction. So if you look in these two directions, you will find that it should be downward side but moving towards right. So the resultant of these two vectors would be something in this direction. Okay, so the resulting vector a minus b would have this geometric interpretation. Okay, now suppose you multiply a vector by a scalar value. Multiply a vector by a scalar value. A scalar means suppose you are just scaling it. Okay. So suppose one vector is represented as a equal to 1 to 3. So you want to find the twice of this vector a. That means you should have the corresponding values of 2a should be twice of the elements of a. Okay. So what would 2a be? That would be twice of a would be your 2, twice of 2 would be 4, and twice of 3 would be 6. So twice of a vector would be 2, 4 and 6. Similarly, if I say 3a equal to 3, 6 and 9, then I am right. Suppose you are given another vector b represented by 3, 6 and 7. So if you are said that find the value of 2a plus 6b, so you will find 2a first. So 2a would be 2, 4, 6 plus 6 of b. So 6 of b would be, first term would be 18, second term would be 6 into 6, 36, 6 into 7, 42. Okay. So if you find the sum of these two, you will get 20, 40 and then 48. Okay. So this is the value of 2a plus 6b when you had these two vectors. Okay. Suppose you are given two vectors of different number of elements. So in that sense, you can't add those two vectors. Even you can't add the scalar of those vectors. That means if they are multiplied by some given scale or given values which are taken from real values, then you can't find the addition of their scalar products. Okay. So in the Leontief model, we saw that a11 x1 plus a12 x2 plus and so on to a1n xn equal to b1. Similarly, a21 x1 plus a22 x2 and so on to a2n xn equal to b2. In the similar fashion, you had an1 x1 plus an2 x2 and so on to ann xn equal to bn. The first subscript represented the number of equations, while the second subscript represented the number of elements. Okay. So you saw that in the previous class. Suppose you want to represent this as a scalar multiplication of vector a and vector x with b1. So you have a vector and x vector. Okay. So a vector is different and x vector is different. So you will have a vector represented as this a1 vector means the first vector and the a2 means the second vector. Okay. So in the first vector you have this column. Okay. So suppose you are representing this column as a vector a1, then you have say vector a1 is, in simplicity, if you can't make it a bold, just put arrow on your symbol so that it can represent a vector. So this a1 vector would be a11, a12 and so on to a2n. and 1. Okay. Similarly, you will have another column vector a2 equal to a21, sorry, a1. Oh, we have a mistake here. So it should be a21. Yes, it should be a12, a22, and so on to a and 2. And again, you have in the similar fashion a n vector equal to what? A what? 1n, a1, a2n, and same as a and n. Okay. And you have vector x equal to x1, x2, x3, and so on to xn. Similarly, you have a vector b equal to b1, b2, and so on to bn. Okay. So if you want to represent this system of equations in the form of vector, then you can write it as vector a1 multiplied with vector x1. Okay. Vector x, that means all this would be multiplied with the corresponding vectors. Okay. So you will have this multiplication, all these first elements are multiplied with x1, so you have vector a1 multiplied with x1. Since we are taking just one of the variable, we are not represented in terms of vectors. Okay. So a1 vector multiplied with x1 plus a2 vector multiplied with x2, and in the similar fashion you get that an vector is multiplied with xn, which equal to vector b. Okay. So this is the representation of what we had already discussed in the last class. Okay. Suppose if we have the example as 3x1 minus 4x2 equal to 10, and second as x1 plus 5x2 equal to minus 3, then you can represent it as 3, and here if there is nothing, then you will have the multiplication of 1 with the given vector. So it's 3 1 multiplied with x1, and again here it's negative, so it would be minus 4, and it is 5 multiplied with x2 equal to 10 and minus 3. Okay. So you want to solve these two system of equations. So what the solution would be? Suppose you want to solve this. So from this first equation and the second equation, suppose if you multiply the second equation by 3, you get 3x1 plus 15x2 equal to minus 9, and the first equation is 3x1 minus 4x2 equal to 10. So taking the negative of all these, you will have minus 19x2 equal to 19. So your x2 would be equal to minus 1. Okay. So if you put that value in the second equation, you will have x1 plus 5 of minus 1 equal to minus 3. So you will have x1 equal to minus 3, and this minus 5, when this will be brought to the right hand side, you will have plus of 5, so you will have x1 equal to 2. So the value is x1 equal to 2 and x2 equal to minus 1. So if you want to say that 3 1 multiplied with say 2 and minus 4 5 multiplied with say -1, then this will equal to 10 minus 3. This is the case of a scalar product of the vector. Or in the other sense, you can say that this vector can be represented as the linear combination of these two vectors. Which two vectors? Suppose this is vector B, this is your A1, this is your A2. So if you say this vector B is a linear combination of vectors A1 and vectors A2, then you will have a linear combination of A1, A2 vector with the value of vector B. So vector B can be represented as a linear combination of these two given vectors A1 and A2. Okay, where for the linear combination you were assigning some weights. Which weights? That weights were the scalar values. और वहीं से आप स्केलर प्रोडक्ट निकालते थे और वहां से स्केलर कॉम्बिनेशन से आप कॉम्बिनेशन बनाकर लीनियर कॉम्बिनेशन निकाल रहे थे. ओके, सो आई होप ऑल दीज थिंग्स आर क्लियर टू यू. ओके, now suppose some operations that you used. Suppose A plus V, these are the two vectors, vector A and vector V. In that sense, if you add vector A to vector B, okay, or if you add vector B and then vector A, in both the scenarios you will have the same resulting vector. That means vector A plus B is same as vector B plus A. Similarly, if you have vector A plus B added first and then you add some vector C, in that case you can just add the vectors B and C first and then add vector A, the result would be same. For this case, suppose vector A is this one and suppose vector B is this, and you have some vector C, so you will have some resultant vector A plus B plus C. In that case, you just took the sum of A and B first, which came to be A plus B this and this C. So A plus B plus C is this resultant vector. So if you look at this, you will have first you add B, then you add C, so you will have the resultant from here, so you will have this as B plus C vectors. In that you have to add A, so either you can add A from here, so you will have initial point here, so you will have something like A plus B plus C. This would be A plus B plus C. Or in another case, if you have this resultant vector as B plus C, so you can add A in it. So if you want to add A in it, then you will have something like say this. So your initial becomes this point, so your resultant would be this A plus B plus C. In both the scenarios of these operations, you find that the length of the vector would be same, plus the direction of the vector would be same. That means these two vectors are same. Length of the vector is said to be the magnitude of that vector. Okay, and another is your direction of the vector. So if these two are same, that means the vectors are equal. Okay, when you have same magnitude and direction, then the vectors are equal. Okay, similarly, if you add a null vector, what is a null vector? Null vector has no magnitude. You can check it from its name of null. That means What is null vector? A vector where it has no magnitude. Suppose in a 3D space you have a vector 0 0 0, that vector is null vector. A vector from the origin to origin itself is a null vector. So if you add a null vector to a vector A, then you will have the vector A. Okay, so just suppose you have this as A and you add this, so you will just end up at that point itself. So you will have the vector A itself. Okay, getting my point? So if you add null vector to this vector, then it's the same vector. If I say that if you add the same vector to this vector, you get twice of A. If you subtract the same vector, then you will get a null vector. Okay, how? If you use this operation, then you will can end up here. So suppose this is your vector A. Okay, this is your vector A. If you want to subtract A, that means you have to go opposite. That means you started from here and end up here. So you will start from here and end up here. So your resultant is 0. That means null. So A vector minus A vector itself is a null vector. Okay. Suppose you have a scalar alpha plus beta multiplied with a vector A. In that case, you will have alpha A vector, so alpha A vector plus beta A vector. Okay, you can try this from the operations or examples that we had already discussed. Okay, suppose if a scalar is multiplied with two vectors, that means suppose your scalar is say t and you have two vectors, say a vector A and vector B, then you can write it as t times A vector plus t times B vector. Okay, this can be the example that we discussed in the Leontief model. Okay, so you can try it by your own, you will get the same things. Suppose you have a vector multiplied with two scalars but in different order. Suppose you try to multiply 2 and 3 and then apply with a vector A. So that means 6A. Similarly, if you tried 2 times 3 of A, you get again 6A. Okay, or you can similarly say you multiply it as 2A multiplied with 3, that would be 6A. In all these three cases, you will end up with the same result. Okay, that means if you have a scalar alpha and another scalar beta, so alpha times beta times vector A would be represented as vector alpha beta times beta A bar, or you can also say this can be written as beta times alpha A bar. You can use another notation, say T and S, so you can have something like say T S multiplied with a vector A bar. Oh, this is our notation is of a scalar, so you will have A bar equal to T A multiplied with S, or you can write T multiplied with S A. Okay, if you just multiply it with a unit vector, okay, then you will have the same vector. That means you will have the same vector. So if you multiply it with 1, then you will get same vector. Okay. So try using this. Suppose you have one example. You have a vector a equal to 1, 2, 3. So if you multiplied it with 1, so 1 times a would be 1, 2, 3 itself. So that would be vector a itself. Okay. But if you look at the unit vectors multiplication, that means vector 1, 2, 3 multiplied with some, say, unit vector, that is unit vector would be represented by some I, j or k. This I vector is unit vector in x space. Okay. And j is for y and k is for z axis. This thing will be discussed when we try matrix operations. So these all things are for today. So just try to revise all these things, and we shall start from the next topic from the next class itself. Okay, take care, bye bye.